Have you ever walked through a bustling city, looked up at a towering skyscraper, or maybe just, felt really comfortable in your own living room and wondered what really goes into shaping these spaces? It's definitely more than just stacking bricks, isn't it? What are the kind of hidden rules and deep plans that create the whole built world around us?
That's a fantastic question to start with because, the structures we use every single day, they are absolutely not accidental. From the smallest home renovation right up to the grandest architectural statements, there's always this really meticulously planned, multi-layered process happening. It's really where those abstract ideas meet, well, tangible reality. And it's not just about looks, it's about safety and function too.
Exactly. And that's what we're diving into today. A really comprehensive journey into the fundamental principles, the key processes, and the essential elements that govern construction and interior design. We're going to try and unpack how a design actually blossoms into a real building, how safety is woven into every single beam and wall, and how spaces are truly crafted for the human experience. We've gathered quite a stack of sources for you, everything from core construction summaries to really detailed excerpts from regulatory frameworks like the National Building Code and the Interior Design Code of the Philippines. Our mission today is to kind of distill the most important nuggets of knowledge from all this material and bring it to life with some vivid, real-world examples. Hopefully you'll walk away with a completely fresh perspective on the buildings you see every day. So let's kick things off with a really bucket question. What is construction? We use the word constantly, but what does it really mean? Our sources suggest it's much more than just the physical act.
You're absolutely right. It goes far beyond just, putting things together. Construction, really at its core, it's the intricate process of translating an abstract design, maybe for a cozy home or a huge commercial complex, into something tangible, a real-world structure. It's such a complex industry, actually, that its name comes from the Latin constructio, meaning to pile up together. What's maybe surprising is that it's not just physical. It's often seen as one of humanity's most intricate industries. It's this unique blend of art, science, and, well, business.
That distinction really shifts how you think about it. So it's not just about hammers and nails then. It's the art of creating a space that works and looks good, the science of making sure it won't fall down, and the business side of managing all the resources, the costs, the people. It covers everything from preparing the ground, before anything else happens, right through erecting the frame, assembling all the bits and pieces, and those crucial final finishing touches. It's how materials are deliberately ordered and put together into a coherent whole.
Absolutely. Think about building a new family home, for example. It's not just the physical work of, say, pouring the foundation or putting up walls. It's the art of envisioning and creating a space that feels welcoming, comfortable, tailored to how that family lives. It's the science that ensures the foundation is sound, the structure can handle, say, local weather conditions or even earthquakes, and the roof won't leak. And it's definitely the business of meticulously managing the budget, getting the right materials, coordinating all the workers, and navigating tons of legal stuff. All those facets really come together to define construction.
That makes perfect sense. So if construction is the how, what it aims to achieve? It sounds like every construction effort, big or small, is basically a project.
Yeah.
How does that differ from, say, ongoing operations, like running a factory?
That's a really crucial distinction. Our sources define a construction project as a temporary endeavor undertaken to create a unique product, service, or result. The key words there are temporary and unique. Unlike, say, a factory that just keeps churning out identical products, a construction project has a definite start date and a clear end date. Once the building's finished and handed over, that specific project is done.
And it's unique, right? Even if you're building tract housing in a subdivision, each house is technically distinct because of its specific plot. Maybe its orientation to the sun or even small tweaks for the client. It's not just a repetitive cycle.
Precisely. Let's think about a common situation. Building a brand new school versus the ongoing maintenance of existing school buildings. Building the new school, that's a project. It has a specific design, a set timeline, a budget, and a clear endpoint when the school opens. The result is a unique new building. But the ongoing maintenance, like repainting classrooms every few years, fixing leaky taps, repairing old windows, that's an operational activity. It's continuous, absolutely necessary work, but it doesn't create a new, unique product in the same way. And that difference fundamentally shapes how you plan and manage each type of effort.
Okay, so for any construction effort to go from just an idea to an actual building, several key components and players have to be in sync. Let's dive into those foundational elements that make a project actually work.
Yeah, and these aren't just random lists. They are really the pillars that define and control the project's reality, making sure it succeeds. First up, the site. This is simply the geographical location, the venue, but its influence is massive.
The site can really dictate almost everything, can't it? I mean, imagine building a high-rise in a super busy city center versus, say, a big housing complex out in a rural area. In the city, you're dealing with tight spaces, maybe terrible traffic for getting materials delivered, strict zoning laws, potentially tricky underground stuff like old pipes or subways. Out in the country, you might have loads more space, maybe easier truck access, but then you might face challenges hooking up utilities or need totally different foundation types because the soil is different. The site just fundamentally shapes the logistics, the rules, even the materials you choose.
Exactly. Then we have the program. This basically captures all the determined needs of the people who will use the building. It acts as the guiding blueprint for the whole design process. It really answers the question, what does this building need to do?
And this is where the human side really comes in strongly. Designing a hospital, for example, requires a completely different program than designing a shopping mall. A hospital's program is all about sterile environments, efficient patient flow, space for highly specialized medical gear, easy emergency access, patient privacy, things like that. A mall, though, it's focused on maximizing foot traffic, creating eye-catching display areas, having flexible spaces for different shops, and providing easy-to-access public amenities. The program dictates the design right from the very beginning.
Following the program, we have the schedule. This lays out the sequence, the timing, and the duration for all the different tasks needed to finish the project. It's absolutely critical for keeping the project flowing efficiently, making sure everything happens in the right order at the right time. And finally, the budget, the financial allocation. This is, well, it's a lifeblood of any project, really. It determines what you can build to what standard and how. These foresight, program, schedule, budget, they're all interconnected. Change one, and it usually impacts the others.
So the project schedule, it's way more than just a calendar, right? It's like the strategic roadmap for turning that design into a real functioning building. What does a typical construction project timeline actually look like, from those first chats to the final walkthrough?
It's quite a fascinating progression, actually. It often moves in phases, from the purely conceptual to the physically complete. It all starts way before any digging happens, in what we call the pre-construction phases. This usually involves initial contract negotiations, then detailed programming and pre-design. Often there's an interior survey, too, to really understand the client's current space or specific needs. Then comes the big moment, the presentation, and critically, the approval of the design concept, getting everyone aligned on the overall vision.
Right, nailing down that big picture idea first. Then from there, we move into schematic design, where those initial concepts start to get a bit more concrete shape. And is this also when a conceptual price estimate happens, leading to that crucial review and approval of the budget estimate, setting the financial guardrails for everything?
Exactly. Once those conceptual and financial frameworks get the green light, the project shifts into the design and documentation phases. This kicks off with design development, where the approved schematics get refined, fleshed out with much more detail. This is typically followed by another review and approval cycle, just to make sure everything's still aligned with the client's vision and, importantly, the budget. The culmination of this whole phase is the massive set of construction documents. These are the detailed blueprints and specifications that the contractors will use to bid on the job and actually build it.
Okay, then comes the really exciting part, I guess the bidding and execution phases. This is where the physical work finally kicks off. It starts with bids and negotiations, right? Where contractors submit their proposals based on those super detailed documents. Then the award contract goes to the chosen contractor. And next comes what you called a critical bottleneck, acquisition of permits. You can't build without them.
That's definitely a common point for delays. Once the permits are finally secured, then you have the mobilization of site. That means setting up the construction site itself, bringing in equipment, setting up temporary offices, storage, etc. Then the actual building work begins under construction administration, where everything is carefully overseen to make sure it matches the plans precisely. And finally, especially for the inside spaces, there's the installation of furnishing.
Let's think about that old office building renovation again. The schedule would break it all down. You'd start with those initial client meetings, the programming, figuring out what the new office needs, the vibe, how many people. Then the design phase architects, interior designers crafting layouts, choosing materials. Then that crucial, often tricky step, permit acquisition. Getting approvals for demolition, new walls, electrical, everything. Missing a deadline here, like for a crucial fire safety permit, that could easily push the whole schedule back weeks or months. Only after all those permits are in hand can you move to mobilization, then the actual demolition and build out, and finally, installing all the new furniture and tech. Each step really depends on the one before it. Budgets. They can feel pretty daunting, but our sources actually break them down into 5 main components, which helps. Let's really try to unpack the difference between hard and soft costs. That seems fundamental to knowing where the money actually goes.
It's an excellent point. Understanding these different cost buckets right from the start gives you so much clarity and control over the finances. So, hard costs, sometimes called direct costs, are all about the tangible, physical elements of construction. This includes the actual raw materials, steel, concrete, wood, drywall, you name it, and the labor directly involved in putting it all together. It also covers fixtures, furniture, and equipment, FF&E. Our sources are specific here. These are generally movable items that don't need a permanent connection to the building's structure or utilities. Think desks, chairs, maybe some appliances. And lastly, TempFacil. That's the cost of setting up temporary facilities on the site offices, storage sheds, fencing, that kind of stuff.
Okay, so if you're building that new apartment complex, the actual concrete for the foundations, the steel rebar inside it, the lumber for framing, the roof shingles, and the wages paid to the masons, the carpenters, the electricians doing the work, those are all definitely hard costs. Even things like the refrigerators or light fixtures, as long as they're not permanently built in, could fall under FF&E hard costs.
Exactly. Then you have the soft costs. These are the indirect expenses, often less visible on the site itself, but absolutely essential for the project to happen at all. This category covers design and consultancy fees, the money paid to your professionals. Architects, engineers, interior designers for their plans and expertise. There's also the project management fee, covering the cost of overseeing and coordinating the entire complex process. Permit fees are another big one, the money paid to the local government for all those necessary approvals.
And you've also got insurance, specifically contractors' all-risk insurance, or CARI, to cover potential accidents or damage during the build. And finally, contingencies. That crucial pot of money set aside for the unexpected, that also falls under soft costs. So, thinking about it simply, the fee you pay the architect for drawing up the plans or the fee you pay the city for the building permit, those are classic soft costs. They aren't physical parts of the building, but you absolutely cannot build legally or professionally without them. It's true for almost any big undertaking, isn't it? No matter how carefully you plan, something unexpected will happen. That's where contingency comes in. So, what exactly is contingency, and why are there different kinds of this just-in-case money?
That's a really critical insight. Contingency is basically the allocated budget set aside for unforeseen issues or possible changes that might crop up during either the design or the construction phase. And what's interesting is that these unexpected circumstances aren't just vague worries, they're often categorized risks that you can actually anticipate to some extent and budget for. Our sources point out several distinct types.
Okay, first there's design contingency. So this is money earmarked for changes needed during the design phase itself, maybe to accommodate new project requirements that emerge, like if the client suddenly decides they need an extra feature after the initial plans are done.
Exactly. Then you have construction contingency. This is the money allocated for unforeseen work or materials that become necessary during the actual building process once you're on site. Think of it as a buffer for the practical realities, maybe hitting unexpected rock during excavation or finding something needs reinforcing.
Next up is owner contingency. This sounds like flexible money that the owner specifically sets aside, maybe to fund additional work or upgrade materials during the project, giving them the ability to make tweaks or add things not in the original plan.
That's right. It gives the owner some flexibility. And finally, there's escalation. This is money specifically reserved to cover significant increases in construction costs, especially for materials, due to things like market fluctuations or inflation. It's a protection against sudden price hikes.
Let's try and picture these in real situations. Say, during excavation for a new office building, the crew discovers an unexpected underground stream that wasn't on any surveys. Dealing with that, maybe diverting the water, maybe changing the foundation design slightly, that would probably come out of construction contingency, right?
Most likely, yes. That's a classic unforeseen site condition.
Okay. Or imagine a homeowner halfway through building their dream house decides they absolutely must have that high-end Italian marble countertop instead of the one originally specified, and maybe add a fancy built-in espresso machine. That kind of upgrade or scope addition would likely draw from the owner contingency fund.
Correct. That's the owner choosing to spend more for something extra or different.
And if, suddenly, there's a major global event that causes the price of structural steel to skyrocket unexpectedly, pushing material costs way up, that kind of unpredictable market-driven increase would typically be covered by the escalation contingency.
Precisely. These different contingency pots are really vital safety nets. They allow projects to adapt to reality, whether it's site conditions, owner choices, or market forces, without completely derailing the budget or the schedule.
Construction definitely has its own language, its own jargon, but understanding these terms can be incredibly useful, making the whole process feel less opaque. Knowing the lingo helps everyone communicate clearly. Let's unpack some of the most common terms you're likely to hear.
Yeah, these terms aren't just, fancy words. They act as really crucial communication tools and often legal instruments too throughout a project. They provide clarity and accountability. First, let's take addendum. An addendum is written information, usually sent out during the bidding process, that clarifies or actually modifies the original bidding documents and makes sure all the contractors are bidding on the exact same updated information.
Okay, got it. Then there's an alternate. What's that?
An alternate refers to additional design options or maybe material choices that are included in the construction documents.
Yeah.
They allow the owner to get multiple cost estimates for different possibilities, giving them flexibility. You might see add alternates for maybe more premium options or deduct alternates for ways to save money.
That makes sense. And crucially, as built drawings, also called record drawings, these sound important.
They are incredibly important. These are the original contract drawings that have been meticulously marked up throughout the construction process to show exactly how the project was actually built, reflecting every change made along the way. They're indispensable for any future maintenance, repairs, or renovations.
And a term everyone's probably heard, a bid.
Simply put, a bid is a formal offer or a proposal, usually including a price, submitted by a contractor to do the work. When a project is put out to bid, that means they're asking contractors to submit their estimates for the time and cost involved.
Let's try to picture these in action. Say a new community center is being put out to bid. The architect might issue an addendum to clarify the specific R value required for the roof insulation, ensuring all bidders factor that in correctly.
Right. And the contractors, wanting to offer options, might submit alternates for the flooring. Maybe a durable, cost-effective vinyl tile as a deduct alternate, and a beautiful, locally sourced hardwood as an add alternate.
Then, years later, when the center needs some plumbing work done, the maintenance team can pull out the as-built drawings. These will show the exact real-world location of all the underground pipes, even if one had to be slightly rerouted during construction due to an unforeseen rock. That information is vital for doing the repair safely and efficiently. Okay, moving on to the legal and administrative side. Construction relies heavily on specific documents and formal processes. Let's look at some critical permits and orders that keep projects compliant and on track.
Yeah, these documents provide essential checks and balances. They ensure compliance with codes and maintain transparency throughout the building's life cycle. Right at the top, you have the building permit. This is the formal written authorization from the government authority, usually local, allowing a specific construction project to go ahead based on approved plans and specs.
And you mentioned earlier, our sources say a building permit is null and void if it's not accompanied by its ancillary permits. So it's really part of a larger package of approvals. Then, once construction is all done, you need a certificate of occupancy. What does that signify?
That's the official document from the local government stating that the building meets all the local occupancy standards, public health requirements, and building codes. Our sources are crystal clear on this. Buildings and structures shall not be used or occupied until a certificate of occupancy is issued. It's the final green light.
Okay. What about changes during construction? That happens, right?
Absolutely. That's where a change order comes in. It's a formal written document signed by both the owner and the contractor that authorizes any alteration to the original scope of work. It could also adjust the contract price or extend the project timeline. It's the official way to manage modifications after the initial contract is signed.
And then there's the Office of the Building Official, OBO. This is the specific government office charged with enforcing the National Building Code.
Exactly. They're the key authority, issuing permits, inspecting buildings, making sure everything's up to code.
We also hear terms like construction management. What does that cover?
Construction management is the overall organization and direction of all the labor, materials, and equipment needed to build the project exactly as designed. It's the coordination function. A consultant is a specialist, maybe an acoustical engineer or a foil expert hired by the owner or designer for specific expertise.
Hmm.
And we already touched on FF&E, furniture, fixtures, and equipment, those movable items not permanently connected.
What about smaller adjustments on site? Is there something less formal than a change order?
Yes. For minor clarifications or changes that don't impact the contract's sum or time, there's often a field order. It's a written directive from the designer or owner's rep to the contractor, usually for quick adjustments to keep work flowing smoothly.
Okay. And what if the contractor needs clarification from the designer?
They submit a request for information, or RFI. It's a formal written question to the owner or designer seeking clarification on the contract documents, the plans, or specifications. It avoids guesswork. Similarly, a request for proposal, RFP, is often used when a main contractor needs a price from a subcontractor for a specific part of the work. It's a request for their estimate or cost proposal.
And finally, shop drawings. These sound very detailed.
They are. Shop drawings are highly detailed drawings, diagrams, installation instructions, maybe even material samples, prepared by the contractor, subcontractor, or supplier. They show exactly how specific components like custom cabinetry or structural steel connections will be fabricated and installed. The architect or engineer reviews and approves these to make sure the contractor's interpretation aligns with the design intent before fabrication begins.
Let's tie these together with an example. A developer finishes a new apartment complex. They absolutely cannot legally rent out any units until the OBO issues the final certificate of occupancy.
Right. And during the construction, maybe a tenant requests a slightly larger closet in their unit, requiring moving a non-load-bearing wall. That modification would need a formal change order signed by the developer and contractor, adjusting the scope and potentially the cost.
Meanwhile, if the site supervisor sees a confusing detail on the window installation plans, they'd send an RFI to the architect asking for clarification before the windows go in, preventing a potential mistake.
Exactly. And the company supplying the prefabricated roof trusses would submit detailed shop drawings showing every cut, angle, and connection plate for approval before they even start manufacturing them. Each document plays a specific, crucial role in keeping the project documented, compliant, and on track.
Okay, beyond the paperwork and the plans, the actual physical work of building relies on a huge range of tools and equipment. Categorizing them helps understand the progression of, well, complexity and power needed on a job site.
That's a good way to look at it. Our sources break them down into 4 main groups, which really shows the spectrum from pure manual labor up to massive machines.
Yeah.
First, you have hand tools. These rely entirely on human power. Think of the basics. A tape measure, a hammer, screwdrivers, a handsaw, maybe chisels. Absolutely fundamental.
Then you step up to power tools. These use power from sources other than just muscle electricity, batteries, compressed air. So this includes things like power drills, circular saws, jigsaws, pneumatic nail guns, staplers, even welding machines. They obviously boost efficiency and capability a lot.
The third category is equipment. These are generally larger tools that employ power supplied by machines, often for a particular specialized job. Examples might include conveyors for moving materials around the site, surveying equipment like transits or levels for precise layout, pumps for moving water, or concrete mixers. They're often bigger and more specialized than handheld power tools.
And finally, the real heavy hitters. Heavy equipment. These are the very large, complex, and powerful machines you see on big projects. This category includes things like bulldozers for moving earth, massive cranes for lifting steel beams or precast concrete panels, excavators for digging foundations, and specialized gear for building roads and highways.
So picture a typical construction site. You might see a carpenter using a handsaw, a hand tool, for a quick, rough cut on a piece of 2x4 framing. But for making lots of faster, more precise cuts, they'll definitely grab a power saw, a power tool. On a larger site, you'll see a huge excavator, heavy equipment, digging out the basement foundation, while nearby, surveyors might be using specialized surveying equipment to ensure the building's corners are laid out exactly according to the plans. Each category really plays a distinct and indispensable role depending on the task and the scale of the project.
Okay, here's where it gets really interesting. We get a glimpse into the cultural and linguistic side of construction. Our sources have this fascinating list of Tagalog terms that are commonly used on construction sites right here in the Philippines. It really shows how practical, everyday language shapes the work itself.
Yeah, what's really insightful is how these vernacular terms often aren't just literal translations. They make complex building components immediately understandable to local workers, bridging the gap between, say, architectural drawings and the actual work on the ground. For instance, a structural column is simply called a post. A wall is often referred to as helij.
Simple and direct. And you have gililan for a girder, solares for a joist, and sahig or suelo for flooring. It's just straightforward, practical language.
Exactly. A beam becomes biga. A horizontal framing stud is called pamabalag bag. For window parts, the window sill is pasamano. The window or door jamb, the side frame, is hamba.
Even common tools get their specific Tagalog names that everyone on site instantly recognizes. Kutsara for a brick or masonry trowel, and pala for a shovel. Essential tools, everyday words.
And it goes beyond just components and tools. There are terms for processes and finishes too, like custarada refers to a plastered course. Politada is the general term for stucco or plaster. Assentada means alignment, making sure things are straight. And hulog is a plumb line, crucial for checking verticality.
This is a fantastic way to see how theory connects to practice through language. Imagine a foreman on a site needing materials moved. They might just say to a worker, "Dahin mo pala sa site ak ilagay ang semento sa mixer," which simply means bring the shovel to the site and put the cement in the mixer. Direct, clear.
Or during a quality check, maybe ensuring columns are straight, they'd say, "Siguro din na posta ituwid." Make sure the column is plumb. This localized language doesn't just speed up communication, it builds a shared understanding right there on the ground, helping the workflow much more smoothly and safely.
We've talked a lot about the act of construction, but what are we actually, building? Let's talk about the structure itself, the building. Our sources give a really clear top-down breakdown of a building's key components, kind of like looking at its anatomy.
Yeah, this approach really shows how interconnected all the different systems are, from the ground right up to the roof. We can basically categorize a building's anatomy into 5 main groups. First, you have the structural components. These are the absolute bones of the building. The building site itself, the foundation supporting everything, and the floor systems that create the different levels.
Okay, structural first. Then you have the envelope and dividers. This sounds like everything that encloses the building and divides up the inside space. So wall systems and where the doors and windows go.
Exactly. That's what separates inside from outside and room from room. Next are the shelter systems. These are specifically designed to protect the building and its occupants from the elements. This includes critical things like moisture and thermal protection, keeping water out and managing temperature, and the overall roof system itself.
Okay, structure, envelope, shelter. Then moving inside, we get to interiors. This covers all the visible stuff, right? The finished work, maybe special features or construction elements that define how the inside looks and functions.
Precisely. And finally, the essential building systems. These are the operational networks that make a building habitable and functional. We're talking electrical systems for power and light, mechanical systems, that's your heating, ventilation, air conditioning, HVAC, and plumbing systems for water supply and waste removal. Every single one of these components, from the deep foundation right up to the paint on the walls, plays a vital role in the building's overall performance, safety, and how it feels to be inside.
Let's think about those shelter systems in a real-world context. Consider the totally different needs for moisture and thermal protection for a building here in a tropical place like the Philippines versus, say, one built in a cold climate like Northern Europe.
Oh, completely different challenges.
Right. Here, the design would prioritize materials and techniques to block heat gain, manage intense humidity, and handle torrential rain, maybe using light-colored reflective roofing, deep overhangs for shade, and excellent ventilation.
Whereas in a cold climate, the focus would be dramatically different, maximizing insulation everywhere, creating airtight seals to prevent heat loss, and designing roofs to handle heavy snow loads. The climate just fundamentally dictates the design of that building envelope. It's absolutely critical.
Every single building, no matter how big or small, has to deal with weight and pressure. Let's unpack this crucial idea of loads and how a building's structural frame is engineered to handle them safely. This is where physics really meets construction.
It's fascinating, isn't it, how these sort of abstract physics concepts become very real forces shaping our environment and keeping us safe. A building's structural frame has several key elements designed specifically to manage these loads. First, the site that's just the ground the foundation sits on. The foundation is the lowest part of the building, partly or fully below ground. Its job is to support the whole superstructure above it and transmit all those loads safely down into the earth. A footing is usually the wider part at the very base of the foundation that spreads the load out.
Okay, foundation first. Then you have the vertical parts, like columns or posts. These are the upright, rigid members designed to take the weight from above the compressive loads and carry them straight down to the foundation.
Right. And then you have the essential horizontal elements. Girders and beams are the rigid horizontal members. Their job is to carry and transfer transverse loads, that's weight spread across their length, like from a floor over to the supporting columns or walls. Joists are usually smaller horizontal members spanning between beams or walls, and they directly support the floor or ceiling. And the floor itself is the level surface we walk on, distributing our weight and the weight of furniture down to the joists and beams below. All these pieces work together like a skeleton to hold the building up.
So what kinds of loads do these structures need to handle? Our sources identify four main types that engineers have to calculate very carefully. First, dead load.
Yep, dead load refers to the fixed, static loads. It's basically the weight of the building itself, its own structure, the exterior skin, walls, windows, permanent equipment like big boilers or AC units, and any other fixed elements.
So, for example, the actual weight of the concrete floors, the heavy steel columns, the roof structure, maybe a big, permanently installed HVAC unit sitting on the roof, those are all dead loads. They're constant. They don't change once the building is up.
Correct. Second type is live load. These are the moving or transient loads. They can change over time and location. This includes things like the occupants, people walking around, furniture that can be moved, equipment that isn't bolted down, and even environmental things like the weight of accumulated rain or snow on the roof.
Okay, so the people milling about in an office building, the desks and chairs they use, maybe heavy filing cabinets that get moved, or a significant buildup of snow on the roof in winter, those are all live loads. They come and go, and the structure has to handle them whenever they're present.
Exactly. Third type, wind load. This is the pressure exerted by wind acting on the building. It can create lateral, sideways forces, uplift forces trying to lift the roof, or even downward pressure. This is especially critical for tall buildings or buildings in very exposed locations.
You can really picture that. A skyscraper in a typhoon-prone city, for instance, has to be meticulously engineered to withstand enormous wind loads.
Absolutely.
Yeah.
It often requires specialized designs like strong concrete cores or extensive steel bracing, just to prevent it from swaying too much or, worst case, failing during a major storm.
And the final category is other load, dynamic load. This sounds like it covers various other forces.
It does. It includes things like impact forces, maybe from something hitting the building,
Mhm.
shock waves, vibrations from heavy machinery operating inside, and very importantly in many regions, seismic load, the forces generated by earthquakes.
Right. Buildings in earthquake zones, like many parts of the Philippines or California, have to be designed very specifically to handle seismic loads.
Yes, often incorporating designs that allow for some flexibility or specialized damping systems that absorb the energy of the earthquake, letting the building move with the ground motion rather than rigidly resisting it, which could cause it to break. Understanding and designing for all these different types of loads, dead, live, wind, seismic, and others, is absolutely fundamental to ensuring a building is safe, stable, and lasts for a long time.
The foundation. It's literally the bedrock of any building, right? The critical link between the structure high above and the earth deep below. Let's dig a bit deeper into the different types and why you'd choose one over another.
That's a perfect way to phrase it, and it raises a good question. Why are there different foundation types, and how does the ground itself really dictate those choices? The foundation, by definition, is the lowest division of the building, partly or wholly underground, designed specifically to support and anchor the superstructure and transmit all its load safely into the earth. Our sources highlight three main types of substructures or foundations.
Okay, first up, slab on fill. This sounds like maybe the simplest. A concrete slab resting directly on the ground.
Pretty much. It's a concrete slab poured directly onto prepared, compacted ground or fill material, rather than being suspended above it. It's very common and often economical, especially under the right conditions. A classic example of slab on fill is a single-story house built on stable, fairly level ground. You prepare the ground, maybe put down a layer of gravel and a moisture barrier, and then pour the concrete slab right on top. It serves as both the foundation and the ground floor structure.
Makes sense. Second type, crawl space. So this is when there's no full basement, but there's still a space under the first floor.
Exactly. It's an unfinished but usually accessible space between the ground and the underside of the first floor joists. It's typically less than a full story high, hence crawl space. A house with a crawl space offers really convenient access for running and repairing plumbing pipes, electrical wiring, and HVAC ductwork without the cost and excavation of a full basement. It's common on slightly sloping lots or in areas where basements aren't typical.
And the third type, the one many people might picture first, the basement. The lower story, partly or fully below ground level.
Right. A basement provides significant additional space, could be living space, storage, utility rooms, whatever. It also creates a deeper, often more stable foundation, which can be beneficial in certain soil conditions, like expansive clay soils, or in colder climates to get below the frost line. For instance, a house built in an area with very cold winters might need a basement foundation to ensure the footings are below the depth where the ground freezes and thaws, which can cause movement. Or a large commercial building might utilize a deep basement for underground parking, mechanical equipment, and extra storage, providing a very solid base for the tall structure above. The choice really depends on factors like soil type, climate, budget, water table level, and what the building needs to do.
From the pyramids to modern skyscrapers, the materials used in construction tell a huge story about technology, resources, and needs over time. Let's explore some of the fundamental building blocks.
It's really fascinating, isn't it? How these core materials have evolved but remain so relevant. Each has unique properties dictating where and how it's used. Let's start with wood. It's been used for literally thousands of years and is still incredibly common. You get it from forests, lumber yards, home improvement stores.
And our sources make a key distinction between hardwood and softwood. Hardwood generally comes from deciduous trees, is denser, heavier, often used for things needing durability, like flooring, walls, ceilings. Softwood comes from coniferous trees, is lighter, maybe used more for framing, doors, windows, furniture.
That's the general idea. Hardwoods tend to be darker, heavier, often more expensive, but can last for ages and might have better natural weather resistance. Think oak, maple, mahogany. Softwoods like pine, fir, or spruce are usually lighter in color and weight, less expensive, and while durable, often need more protection if exposed to weather. They're great for structural framing inside walls. It's also important to be aware of wood defects knots, splits, warping, which can occur naturally or during processing. Some add character, but too many can weaken wood. And timber is just the general term for wood that's been processed and is suitable for building.
So, as a quick example, for the flooring in a busy shop or restaurant, you'd probably want a really durable hardwood like oak or maple to stand up to all the foot traffic.
Definitely. But for the hidden 2x4s framing the walls inside that same building, a lighter, more economical softwood like pine or fir would be perfectly suitable and cost-effective.
Okay, next up, concrete. Everyone knows concrete. It's everywhere.
It is. And it's a composite material, remember, made by mixing cement, which acts as the binder, aggregate like sand and gravel, and water. Its strength comes from a chemical reaction called hydration, where the cement reacts with water and hardens, binding the aggregate together. The key property we measure is its compressive strength, how well it resists being crushed. The mix is critical. The ratio of water to cement has a huge impact on the final strength and how easily it can be poured and worked.
Right. So when they're pouring a big concrete foundation slab for a building, getting that water-cement ratio just right during mixing is absolutely crucial.
Absolutely. Too much water weakens it, too little makes it impossible to place properly. Both are bad news for the structure.
Okay, what about metal? Seems like another fundamental category.
Definitely. Broadly, we categorize metals used in construction into ferrous and non-ferrous. Ferrous metals have iron as their main component. The big advantages are usually their strength, durability, ductility, meaning they can deform without breaking easily,
Right.
high tensile strength, resisting pulling forces, and they can be treated to resist corrosion, like galvanizing steel. Steel is the prime example here.
And non-ferrous metals. They contain little or no iron.
Correct. Like aluminum, copper, zinc, lead. Their advantages often include attractive colors, lower density, lighter weight, excellent electrical and thermal conductivity. They're often easier to fabricate, and they generally have very high natural corrosion resistance.
So to picture the difference, the massive structural frame of a skyscraper would almost certainly use ferrous steel because of its incredible strength-to-weight ratio and tensile strength, allowing it to carry huge loads.
Right. But for something like window frames or decorative exterior panels, where corrosion resistance, lighter weight, and maybe a specific color are more important, you'd likely choose a non-ferrous metal like aluminum.
Okay, moving on to plastic. Maybe not the first thing people think of in construction, but it seems to have some unique advantages.
It really does. Plastic offers inherent corrosion resistance, which is fantastic for things like pipes carrying waste or chemicals. It's also naturally impermeable and leak-proof because of its molecular structure, making it great for moisture barriers. Many plastics can also be formulated to be fire-resistant by adding specific compounds, which enhances building safety. And importantly, many plastics are quite flexible and have good anti-vibration properties, meaning they could absorb shocks or movement, which can even be useful in some seismic designs.
Okay, so practical examples. You see plastic PVC pipes used for plumbing all the time, right? Especially for drain lines where corrosion resistance matters.
Exactly. Or you might find thin plastic sheeting used as a vapor barrier inside walls or under concrete slabs to stop moisture migration. And increasingly, you see things like PVC window frames, which offer good durability and weather resistance with less maintenance than wood.
All right, final category here, building boards. This sounds like a pretty diverse group of engineered sheet materials.
It is. There are many types. Plywood is a classic thin layers, or veneers, of wood glued together with the grain direction alternating in each layer. This gives it incredible strength in all directions. Insulating fiberboard is made from wood or other plant fibers combined with a binder, primarily used for, well, insulation.
Then you have things like chipboard or particle board. These are made from smaller wood particles or chips mixed with resin and pressed into sheets, often used for furniture cores or subflooring.
Right. Gypsum board, widely known as drywall or plasterboard, has a core made of gypsum plaster, sandwiched between heavy paper or fiberglass mats. Its key benefit is fire resistance. And plastic foam boards, usually made from polystyrene or polyurethane, are very lightweight, rigid boards used mainly for thermal insulation. You see them on walls, roofs, and around foundations.
So as a quick example, those interior walls in most modern houses and offices, they're typically covered with gypsum board because it's relatively inexpensive and provides good fire resistance.
Correct. And the flat surface under your carpet or wood flooring, that's often plywood or maybe OSB, a type of particle board, providing a strong, stable base. And those rigid pink or blue boards you sometimes see on the outside of new houses before the final siding goes on, those are often plastic foam boards being used for exterior insulation. Each type of board is engineered for a specific job.
Okay, let's shift gears now and talk about the rulebook. How are these huge, complex construction projects actually governed and kept safe? The National Building Code of the Philippines, PD 1096, is central to this. We're using it as a detailed example to see how these regulatory frameworks function.
And it's a really important question. Why do we need such a strict regulatory framework for something as basic as building? It really boils down to protecting public safety, ensuring structural quality, and promoting organized development. In the Philippines, the Department of Public Works and Highways, DPWH, is the main agency responsible for administering and enforcing this code, though they often delegate the day-to-day enforcement to local building officials.
And these building officials sound like key figures on the ground. They're the ones responsible for enforcing the code locally, right? Issuing permits, inspecting buildings during construction, ordering fixes if things aren't right.
Exactly. And to ensure they're qualified, they generally need to be licensed Filipino architects or civil engineers with a good number of years of professional experience.
The DPWH also sets up a Technical Review Committee, TRC. What's their role?
They review more complex aspects, plans, specifications, requests for variances from the code, and they issue certificates of compliance. Regarding funding, our sources mention that a portion of the income from fees collected for permits goes directly to support the local building official's office operations. The rest typically goes to the local government unit's general fund. It helps make the system self-sustaining.
And obviously, there have to be penalties for violations. What kind of things can lead to trouble?
Oh, significant fines can be levied for doing work without a permit, making unauthorized changes to approved plans, ignoring orders to stop work, or occupying a building before getting that final certificate of occupancy. There are even hefty surcharges like 100% of the permit fees if you start construction before getting a permit. It really underscores how seriously compliance is taken.
So let's imagine a real situation. A local building official is doing a routine inspection on a new shopping mall construction site.
Wow.
If they discover the contractor is using, say, a cheaper, lower-grade steel rebar than what was specified in the approved structural plans, and that steel doesn't meet the code requirements for that type of structure,
The building official would have the authority to issue an immediate work stoppage order for that part of the project.
and if the contractor ignores it or doesn't fix the problem,
They'd face substantial fines, potentially those surcharges too, and wouldn't be allowed to proceed until it's corrected. This shows the code's teeth. It's directly aimed at ensuring public safety and making sure buildings are built according to approved, safe designs.
permits. They often feel like just red tape, but they're clearly critical safety and compliance checkpoints. What's actually needed to get a building permit in the Philippines? Based on our sources, it sounds like a comprehensive process.
It really is. And what's striking is the sheer amount of detailed documentation and professional sign-offs required before you can even think about breaking ground. Building permits are mandatory for pretty much any construction, alteration, repair, conversion, or demolition. And remember that crucial detail. A building permit is considered invalid if it's not accompanied by all the necessary ancillary permits. It's a whole package.
Right, a package deal. So the application process itself involves filling out specific forms and submitting them to the local office of the building official, OBO.
And the required documents list is extensive. First, you need proof of property ownership. That usually means a certified true copy of the property title, maybe an original certificate of title, OCT, or a transfer certificate of title, TCT, along with things like tax declarations and receipts, or maybe a lease contract if you're not the owner. You have to prove you have the right to build there.
Okay, proof of ownership. But then comes the design documentation itself. You need multiple sets, usually 5 of plans and other documents, and they all have to be signed and sealed by a whole team of licensed professionals.
That's right. It's a collaborative effort. You need sign-offs from a licensed geodetic engineer for site surveys, an architect, a civil engineer for structural design, a professional electrical engineer, a professional mechanical engineer, a sanitary engineer, a master plumber, and sometimes even an electronics engineer, depending on the project's complexity.
Wow, that's a lot of experts involved. What kind of specific documents are we talking about?
You need detailed architectural plans. These include floor plans, elevations, sections, site development plans, and crucially, details on interior design aspects, accessibility features for persons with disabilities, and fire safety plans. Then, comprehensive civil structural documents, which include the structural analysis, results from soil tests like boring and load tests, and seismic analysis calculations, plus separate detailed documents for electrical systems, mechanical systems like HVAC, sanitary systems, plumbing, geodetic surveys, and electronic systems if applicable, like fire alarms or communication systems. On top of all that, you often need clearances from other agencies, like a locational clearance from the local zoning administrator, confirming the proposed use is allowed in that area.
Okay, so once you've gathered all that, what about issuance and validity?
The OBO is supposed to issue the permit within 15 days after you've paid all the required fees. But the permit isn't valid forever. It typically expires if construction doesn't start within 1 year from the date of issuance, or if work stops for more than 120 days. And for inspection and supervision during the build, the owner is required to hire a licensed architect or civil engineer to provide full-time inspection and supervision. A detailed logbook must be kept at the job site documenting progress and inspections. Once finished, a certificate of completion is submitted to the building official.
Let's picture that developer planning a new commercial building again. Before starting any physical work, they have to gather that massive package. Structural designs from the civil engineer, electrical layouts from the electrical engineer, interior plans maybe from an interior designer signed off by the architect, all signed and sealed.
Exactly. All compiled and submitted to the OBO just to get the main building permit. The sheer volume and specialization required really highlights the meticulous planning and professional coordination needed to ensure a building is safe, functional, and compliant before construction even begins.
Building safety often comes down to the details how key structural elements are designed and built. Let's look at how the code addresses things like vertical openings, elevator shafts, stairwells, and the integrity of floors and roofs.
Yeah, and this raises the question, how do these specific rules directly contribute to better fire safety and structural stability in the real world? For vertical openings, like elevator shafts or escalator enclosures, the code generally mandates construction with materials providing not less than a 2-hour fire resistance rating. This means the walls surrounding these shafts are designed to contain fire for a significant time. Furthermore, for elevator shafts that extend through more than 2 stories, they need approved ventilation that leads directly to the main roof. This helps vent smoke and heat upwards and out rather than letting it spread horizontally to other floors.
So those fire ratings are literally about buying time and preventing fire spread. What about floor construction?
The materials and methods used for floors must comply with the requirements for the specific fire zone the building is in and its type of construction. Critically, all floors must be framed and securely tied into the building's main framework and supporting walls. This helps prevent beams and girders from buckling sideways under load and ensures the whole structure acts as an integrated system. And for roof construction and covering, Similar principles apply.
Yes.
The roof covering material must meet specific fire retardant standards based on the building type. Combustible insulation can be used, but only if it's properly covered by approved roofing materials. Roof trusses, the triangular frameworks often used to support roofs, must be securely framed and tied into the rest of the structure. Joints need to be tight, and appropriate bracing must be used to prevent sagging or instability over time. The code also requires proper flashing and counterflashing. These are strips of weatherproof material installed where the roof meets vertical surfaces, like walls or chimneys, to prevent water from seeping in at those joints, absolutely crucial for preventing leaks and long-term water damage.
And things like overflow drains and scuppers, especially on flat or low-slope roofs.
Essential. They must be provided where needed to prevent water from ponding on the roof, which can add a huge amount of unexpected weight. Any concealed piping associated with these must follow the National Plumbing Code standards.
Let's picture that multi-story office building again. The walls around the elevator shaft aren't just drywall. They're built with specific fire-rated materials, maybe concrete blocks or multiple layers of fire-rated gypsum board, and the doors are fire-rated, self-closing assemblies.
Right. This creates a protected shaft designed to stop fire from easily jumping from one floor to the next, providing a safer path for escape or firefighter access.
And the large flat roof of a commercial building would be engineered with multiple drains and maybe scuppers, openings through the parapet wall, to ensure heavy rainwater can get off quickly.
Exactly. Preventing water buildup is critical because that water adds significant weight, a live load, that the structure wasn't necessarily designed for if it accumulates too deeply. These details really demonstrate how the code translates into tangible safety features.
Okay, beyond the bones of the structure, the building code also gets into how the interior environment should work, things affecting comfort and safety inside. Let's talk about how the code tackles things like sound transmission, minimum room sizes, and even what kind of finishes are required.
It's quite fascinating how detailed these regulations get, really aiming to improve the actual lived experience inside a building. They address both functional needs and even sensory aspects. For instance, sound transmission. The code requires that walls, partitions, and floor-ceiling assemblies that separate dwelling units, like apartments, or separate dwellings from public areas, like corridors, must meet a minimum sound transmission class, or STC rating. This is all about providing acoustic privacy.
So in practice, that means the wall between your apartment and your neighbors needs to be built in a specific way, maybe with insulation inside, or multiple layers of drywall, or staggered studs specifically to dampen the sound traveling through it so you don't hear everything next door.
Exactly. It's about creating a reasonably peaceful environment. Then there are strict rules about interior space dimensions. Habitable spaces, like living rooms or bedrooms, but not kitchens, generally need to be at least 7 feet, about 2.1 meters, in any plan dimension, so no super narrow, unusable rooms. Kitchens have their own rule. They need a minimum clear passageway of 3 feet, about 0.9 meters, between counterfronts, appliances, or walls. This ensures you can move around safely and efficiently while cooking.
And ceiling heights are specified too, to avoid feeling like you're in a hobbit hole.
Pretty much. Habitable rooms typically need a minimum ceiling height of 8 feet, about 2.4 meters. Even spaces like corridors, bathrooms, kitchenettes, storage rooms, and laundry areas have their own minimums, usually a bit lower, but still ensuring adequate headroom and air volume. There's also often a minimum living unit area specified for new residential construction, ensuring a baseline level of overall space.
And finally, room finishes. The code even gets into what the surfaces should be like.
Yes, mainly for hygiene and maintenance. Floors in habitable rooms generally need to be smooth, hard-surfaced, and easily cleanable. Walls and ceilings should also be smooth, cleanable, and free from excessive cracks or holes where dirt or pests could accumulate.
So let's imagine an interior designer planning a small studio apartment in a big city. They have to make sure that main living area meets that minimum 7-foot width. They need to lay out the kitchenette so there's at least 3 feet of clear floor space between the sink counter and the fridge.
And they have to ensure the ceiling height hits that 8-foot minimum in the main space. All these detailed requirements work together to make sure that even compact living spaces provide a basic level of comfort, safety, and usability for the people living there. It really shapes the human experience inside.
Even the parts of a building we don't usually see, attics, crawl spaces, need to be accessible for maintenance and safety checks. The code actually has rules about accessing these unoccupied spaces.
Yeah, and this highlights a really crucial point. These access requirements might seem minor, but they are vital for the building's long-term health and functionality. They allow for proactive maintenance and inspection of hidden systems. For crawl spaces, our sources say there needs to be at least one access opening of a minimum size, often around 18 by 24 inches, or 457 by 610 millimeter.
Yeah.
This opening has to be readily accessible, usually from the outside, and kept clear of obstructions.
Right, so if a plumber needs to get under the house to fix a leaky pipe in the crawl space, that access opening has to be big enough for them to actually get in and move around reasonably safely.
Exactly. Similarly, for attic spaces, if they have a clear height of over, say, 30 inches, 762 millimeter, there needs to be an access opening, maybe a hatch in the ceiling or a small door of a minimum size, often around 20 by 30 inches, 562, 732 millimeter. This ensures that someone can get into the attic to inspect or maintain things like insulation, electrical wiring, or maybe HVAC components located up there.
And what about access around mechanical appliances themselves, like furnaces or water heaters?
The code generally requires adequate clearance for both operation and maintenance. Typically, this means a minimum of 30 inches, 762 millimeters, of clear, unobstructed space in front of and around the appliance.
Okay, so the technician has room to work safely and effectively.
Precisely. It prevents situations where essential equipment is crammed into a tiny closet where it's almost impossible to service. For instance, if a home has critical electrical junction boxes or HVAC ductwork running through the attic, the code mandates that properly sized access panel so those systems aren't just hidden away and forgotten until something goes wrong. These seemingly small access rules significantly contribute to a building's overall safety, maintainability, and operational efficiency over its entire life.
Okay, moving up high now. Features on the roof like penthouses or housings for equipment, they also have specific rules about their size, purpose, and construction. It's not just a free-for-all up there.
Absolutely not. It's fascinating how urban planning considerations and safety regulations work together to limit these rooftop additions. It's about maintaining structural integrity, fire safety, and preventing misuse. Regarding height limits, our sources indicate that projections above the main roof, excluding certain types of construction, generally can't exceed about 8.4 meters, roughly 27.5 feet, if they house things like water tanks or elevator machinery extending to the roof. For other purposes, the limit is usually lower, around 3.6 meters, about 11.8 feet.
And there are strict rules about prohibited uses, too. What can these rooftop structures actually be used for?
Our sources are very clear. Penthouses or similar structures projecting above the roof are intended only for sheltering mechanical equipment or enclosing vertical shaft openings like stairs or elevators. If they're used for anything else, say turned into a private office, a small apartment, or a rooftop lounge, the code classifies that space as an additional story. And that triggers much more stringent requirements regarding exits, fire resistance, structure, etc., significantly impacting the design and cost.
Ah, so you can't just call a top floor a penthouse to get around the rules for a full story. What about size? Is there an area limit?
Yes, the total combined floor area of all penthouses and other roof structures generally cannot exceed 1/3 of the area of the supporting roof below. In terms of construction, their walls, floors, and roofs usually need to meet the same requirements as the main building below, although there might be some exceptions regarding fire-resistive construction if they are set back sufficiently far from adjacent property lines.
And what about really tall things like towers and spires?
If they're enclosed, their exterior walls usually have to match the requirements of the building they're attached to. And if they extend significantly high above ground level, say over 20 meters, their structural framework typically must be made of robust non-combustible materials like iron, steel, or reinforced concrete.
Let's picture that new condominium building again. It has a utility room on the roof housing the elevator machinery.
Okay.
That room, being classified as a penthouse, must strictly adhere to those height and area limits set by the code. And critically, the developer can't just decide later to convert that space into a fancy private gym for the top floor resident, for instance, without having designed and permitted it as an additional story from the beginning, meeting all the associated tougher code requirements. It prevents sneaking in extra habitable space under a different name. Fire safety is obviously paramount in building design. The code is very explicit about where automatic fire extinguishing systems like sprinklers are required. This isn't just a nice to have, it's a legal necessity, often driven by tragic lessons from the past.
That's a really critical point. When you connect this to real-world events, tragedies like the ozone disco fire here in the Philippines, which tragically killed 162 people, serve as devastating reminders of what can happen with inadequate fire safety. They underscore the absolute importance of enforcing these regulations. The code mandates automatic fire extinguishing systems in specific required areas. This typically includes habitable spaces, including basements and cellars, that exceed a certain floor area, like 200 square, or have an occupant load over a certain number, like 20 people. It also applies to specific types of occupancies known to have higher risks, like large assembly venues, groups E, H, I in the code.
Okay, sprinklers in certain areas. What about standpipes? These are the pipes firefighters connect hoses to, right?
Exactly. There are two main types, dry and wet. Dry standpipes are usually required in buildings that are 4 or more stories high, but maybe have smaller floor areas. They're basically empty pipes with connections at various levels, typically near stairways. Firefighters have to pump water into them from their truck.
And wet standpipes, are they always filled with water?
Yes, that's the key difference. Wet standpipes are designed for more immediate use, kept constantly filled with water under pressure. The code specifies the required internal diameter to ensure they can deliver a minimum flow rate, like 190 liters, at a minimum pressure, like 2 kilojoule female phase. The number and location of wet standpipes are carefully determined so that all portions of the building are within a certain distance, like 6 meters, of a nozzle attached to a standard length hose, like 23 meters. This ensures rapid response capability everywhere. Specific locations are mandated for high-risk occupancies. The water supply for wet standpipes needs to be reliable, either from a strong street main or a dedicated tank large enough to supply water for a minimum duration. For example, 1,500 liters for 10 minutes, often backed up by dedicated fire pumps.
And the automatic fire extinguishing systems themselves, the sprinklers, must be installed in those specified places we mentioned earlier. Thinking about the terrible Manila Central Post Office fire, where the fire reportedly started in the basement.
That tragedy really underscores the need for robust, functional fire extinguishing systems, especially in large, complex, or older buildings which might contain significant amounts of flammable materials, and where fires starting in lower levels can be hard to detect and fight initially.
As a clear example, imagine a large modern convention center. As a high-occupancy public assembly space, it would absolutely be required to have multiple wet standpipes strategically placed throughout its exhibit halls and meeting rooms.
These standpipes would be located so that any point within that vast building is easily reachable by a firefighter deploying a standard fire hose connected to the standpipe. This isn't just a suggestion, it's a critical, legally mandated safety feature, often informed by analyzing past incidents, designed to enable a rapid and effective response to suppress a fire and protect lives.
It's amazing how detailed the code gets. Even very specific building uses like old-school motion picture projection rooms have incredibly detailed safety requirements. It shows how regulations adapt to unique hazards.
That's a great point. It's fascinating to see the code tailoring rules for specialized uses, recognizing specific risks like the highly flammable nitrate film stock that was common when many of these rules were first written. For construction, these projection rooms had to be built with materials providing not less than 1 hour fire resistance throughout. All interior finishes had to be non-combustible. There were also minimums for ceiling height, 2.4 meters, and floor area, 7 square meters, plus more per additional machine, to ensure adequate space and prevent overcrowding with hot equipment.
And what about getting out in an emergency? Exit requirements.
Very specific. At least 2 doorways were required, located apart from each other, meeting minimum width, 750 millimeter, and height 2 meter standards. These doors had to be self-closing fire assemblies with a 34-hour rating, swinging outwards towards proper exits, and crucially, they could not have any latches, allowing for push-open escape even if your hands were full or visibility was low.
Okay, no latches, just pushed open. What about the openings for the projectors themselves, the ports and openings?
Those projection ports, observation ports, etc., also needed strict safety measures. They had to be fitted with specialized shutters, usually made of sheet metal. These shutters needed fusible links designed to melt in heat and automatically close the port, plus manual closure mechanisms located both near the port and near the room exits, providing multiple ways to seal the room off quickly if a fire started.
And ventilation seems incredibly detailed, too. An inlet for fresh air.
Yes, a dedicated fresh air inlet from the exterior was required, of a minimum size, protected with wire netting, and located near the floor, drawing air from a source away from other building vents.
And the exhaust, getting rid of heat and fumes.
Critically important. Mechanical exhaust systems were mandated to draw air directly from each arc lamp housing, which got incredibly hot, and from the room itself. This exhaust had to be ducted directly outdoors through an incombustible flue used only for the projection room. The exhaust system had specific capacity requirements based on the number of lamps and the room size. It had to be controlled from inside the room, with pilot lights to show it was running. Importantly, no dampers were allowed in these exhaust ducts, ensuring they were always open. And this system had to be completely separate from any other ventilation or air conditioning system in the building. The ducts themselves had to be incombustible and kept clear of any combustible materials or properly insulated.
So picturing an old cinema again, that projection booth wasn't just a room, it was practically a fire-rated vault.
Essentially.
It would have those specialized fire doors, maybe heavy steel ones, designed to automatically swing shut. And it would have its own dedicated, powerful exhaust system, totally separate from the main theater's AC, sucking heat and any potential fumes directly outside.
This meticulous separation and fire-rated construction were absolutely vital to prevent a fire, starting with a flammable film or hot equipment from rapidly spreading smoke and flames into the main auditorium, protecting hundreds of people.
How a building is actually put together, its materials and structure, directly affects how well it resists fire. The code classifies buildings into different types of construction, each with specific fire resistance standards. This seems fundamental to safety.
It really is, and this raises a critical point. Why are these classifications so important? They essentially dictate the minimum level of fire safety built into the structure, influencing material choices, design details, and ultimately the time available for occupants to escape in a fire. Our sources outline 5 main types. Type 1 is described as purely wooden construction, the most basic and least fire-resistant. Type 2 is also primarily wood construction, but it incorporates some fire-resistive materials or uses fire-retardant treated wood to improve its performance compared to Type 1.
Okay, so types I and 2 are mainly wood. What about type 3?
Type 3 buildings are a mix of masonry and wood. While the internal structural elements can be wood or other permitted materials, the key requirement is that the building must achieve a minimum of 1 hour fire resistance throughout, and its exterior walls must be made of incombustible materials like brick or concrete block. For example, think of a traditional multi-story shop house or a small apartment building with a masonry exterior but wooden floors and internal partitions. The design aims to contain a fire within a single unit or floor for at least an hour.
Moving up in resistance, type 4 construction.
Type 4 buildings are significantly more robust, built primarily with steel, iron, concrete, or masonry structural elements. The walls, ceilings, floors, and permanent partitions must generally be of incombustible, fire-resistive construction, usually at least 1 hour rated. However, there's a bit of flexibility. Non-load-bearing interior partitions can use fire-retardant treated wood framing. A good example might be a modern warehouse or a light industrial building with a steel frame, concrete floors, and masonry exterior walls, possibly with some internal office partitions framed with fire-retardant wood.
And finally, type V. This sounds like the highest level of fire resistance.
It is. Type B construction requires a minimum of 4-hour fire resistance throughout the structure. All structural elements, frames, floors, roofs, walls, must be made of steel, iron, concrete, or masonry. Think of a modern high-rise office tower or a large hospital. Its entire structural system would typically be steel and concrete, meticulously designed and protected. For example, steel beams encased in fire-resistant material to withstand a severe fire for at least 4 hours. This provides the maximum time for evacuation and firefighting in very large or critical buildings.
So the fire resistive requirements vary significantly based on the type.
Absolutely. The code summarizes minimum hourly ratings for different building elements depending on the construction type. For example, exterior walls might range from 1 hour for types 2 and 3 up to 4 hours for types 3 and V. Interior bearing walls, floors, and structural frames also have increasing requirements, typically from 1 hour up to 3 hours for type V elements. Even exterior doors and windows usually need a 1 hour rating across all types.
And what about the finishes inside the paint, wallpaper, ceiling tiles? Are they regulated too?
Yes, interior ceiling and wall finishes are classified based on their flame spread characteristics, often determined by a standard tunnel test. Materials must also meet limits on smoke density. Any materials that need to be flame-proofed must achieve a low flame spread rating, for example, 50 or less. It's also worth remembering that broader fire safety standards, covering everything from the structural framework to exits, stairs, and roof assemblies, are often governed by more comprehensive fire codes, like the Philippine Fire Code, RA 9514, which works in conjunction with the building code.
Where a building is located geographically can profoundly impact how it needs to be built, particularly concerning fire risk. Let's talk about fire zones. This sounds like urban planning meeting building codes.
That's exactly what it is. What's insightful here is how city planning integrates with building regulations specifically to manage and prevent large-scale fires, especially in dense areas. The fundamental purpose of designating fire zones is to strategically manage, prevent, control, and suppress potential fires in populated areas by dictating minimum construction standards based on density and risk. A key rule: if a building straddles more than one fire zone, say, part of it is in a more restrictive zone and part in a less restrictive one, if more than a third of its floor area is in the higher risk zone, the entire building is generally required to meet the standards of the more heavily restricted zone. No cutting corners.
That makes sense for safety. What if you physically relocate an existing building into a fire zone?
It must be brought up to meet all the standards required for new construction in that specific zone. This applies even to modern pre-engineered or prefabricated buildings if they're moved. There are also restrictions on existing buildings within fire zones. Generally, you can't significantly enlarge, alter, or repair an existing building if it doesn't already meet the current standards for new construction in that zone. However, there are specific exceptions.
Exceptions like what?
Well, for instance, minor repairs or alterations might be allowed if their cost over a year is below a certain percentage of the building's value, and critically, they don't increase the fire hazard or use more combustible materials. Additions might be permitted if they are physically separated from the non-conforming original structure by proper firewalls or barriers, and restoring damage, like from a fire or storm, is often allowed, but usually only if the damage doesn't exceed a certain percentage, like 20% of the building's replacement cost. It tries to be pragmatic while still prioritizing safety upgrades over time.
So how are these fire zones designated? Who decides, and what are the categories?
The designation is typically the responsibility of the local government unit, LGU. Our sources describe three main types. First, non-fire restricted zones. These are areas where minimal or no specific fire resistance is required for construction. Think rural areas, sparsely built-up country locations where buildings are far apart. Materials like bamboo, nipa, traditional wood, allowing types 1 and 2 construction, are common. Widespread fire is less of a concern due to spacing.
So a remote farming village with houses made of local bamboo and nipa thatch, spaced well apart, would likely be in a non-fire restricted zone.
Exactly. The risk of fire spreading rapidly from building to building is low. Second category, fire restrictive zones. In these zones, exterior walls must typically meet at least a 2-hour fire resistance rating. These are common in suburban areas, towns, or less dense parts of cities. Construction usually needs to be type 2, 3, or 4, with a minimum 1-hour fire resistance rating generally required throughout the building structure.
Okay, so maybe a typical suburban housing development with homes built using concrete block or brick veneer exteriors and maybe fire-rated drywall inside would likely fall into a fire-restrictive zone, a higher level of safety for a denser community.
Correct. And the third category, highly fire-restrictive zones. These demand the highest level of fire safety. Construction must be highly fire-resistive or non-combustible throughout, often requiring 3 to 4-hour fire-resistive assemblies, including the exterior walls. Only the most robust construction types, like types 4 and V, are typically permitted here.
So this would be your dense urban core, areas with high-rise office buildings, crowded commercial districts, maybe large industrial facilities packed closely together.
Precisely. In these highly fire-restrictive zones, the potential for a catastrophic, rapidly spreading fire is greatest due to density, building height, and occupancy, so the construction standards are the absolute strictest, mandating multi-hour rated steel and concrete structures.
It's also interesting that the center lines of streets can sometimes be used as the reference point, like an adjacent property line, for measuring required setbacks or distances in these zones.
Yes, that acknowledges the fire break that a street provides. And even temporary building structures like construction site offices or temporary event stages are permitted within fire zones, but only with special permits for a limited time, and they still must adhere to appropriate safety requirements for that zone.
For example, those temporary viewing stands set up for a festival in a park located within a fire-restrictive zone would need a special permit.
And despite being temporary, they'd likely need to incorporate fire prevention measures, maybe use fire-retardant materials, and have clear evacuation routes, ensuring public safety even for a short-term structure. It shows how fire safety considerations permeate almost every aspect of building and land use planning.
Okay, we've talked a lot about the structure, the shell, the safety codes, but it's not just about erecting a building, it's about shaping the spaces inside. This is where interior design and its own specific code, the National Interior Design Code of the Philippines, really comes into focus.
And this highlights a really crucial distinction that's often overlooked. Interior design isn't just about making things look pretty. It's a regulated professional practice that profoundly impacts the safety, functionality, accessibility, and overall human experience within a building. Our sources define the National Interior Design Code of the Philippines, ID Code, quite comprehensively. It's described as the science and art of planning, specifying, selecting, and organizing the surface finishes and materials including furniture, furnishings and fixtures, and other interior design elements, for the purpose of the interior space allocations to suit, enhance, and meet the intended function, movement, and character for which the interior of the building is designed. It's a very thorough definition.
That really covers a lot. So the scope of professional practice for a licensed interior designer is quite broad then. It's not just picking colors and furniture.
Not at all. It includes things like providing consultation and advice, developing budgetary estimates for interior work, creating schematic designs and developing them further, preparing detailed contract documents, producing plans, drawings, and specifications for interior construction and finishes, and even teaching interior design principles.
And how does this ID code relate to the National Building Code we've been discussing?
That's a key point. The ID code is explicitly designed to be consistent with, complementary to, and fully compatible with the National Building Code, NBC, and other related codes like electrical, plumbing, fire codes. And here's the important rule. If there's ever a conflict or overlap between the provisions of different codes, the most restrictive provision always governs. This ensures that the highest standard of safety or quality is always applied.
And didn't we mention earlier that interior design is listed as one of those critical ancillary permits required for a main building permit to even be valid?
Yes, that's correct. It's listed right alongside architectural, civil structural, electrical, mechanical, sanitary, plumbing, and electronics permits. This really elevates the status and regulatory importance of professional interior design in the Philippines. It formally recognizes its essential contribution to creating safe, functional, and compliant built environments, integrating it fully into the overall permitting and design process.
Good interior design goes way beyond just aesthetics, doesn't it? It's fundamentally about how spaces feel and function naturally. Things like light and ventilation seem absolutely basic but crucial.
They are fundamental. And it's fascinating how these regulations, like those in the ID Codes Chapter 4, often prioritize using natural means first, connecting the building's design back to its environment. The general requirements state that buildings need to be designed, constructed, and equipped to provide adequate light and ventilation for occupants. Habitable rooms generally need to face an approved street or public alley to ensure sufficient exposure. Importantly, you can't make alterations later that would reduce a room's size or its window area below the required minimums. Nor can you enlarge a building in a way that compromises required courtyards or yards needed for light and air.
Okay, so protecting access to light and air. How does the code encourage natural ventilation specifically?
It encourages designs that maximize natural air movement. This can include strategies like positioning openings for cross-ventilation, incorporating traditional elements like ventanillas, small operable openings below main windowsills, transoms, openings above door heads, or using fixed louvers or even perforated wall sections to allow airflow.
And there are rules about the size of window openings too.
Yes. Rooms intended for natural ventilation generally must have windows with a minimum clear ventilating area, often calculated as a percentage, maybe 10%, of the room's floor area. This ensures enough air can actually get in and out. If traditional windows aren't feasible, skylights can be used for ventilation, but they need to provide an equivalent open area, possibly with fixed louvers.
What about situations where natural ventilation isn't enough, like rooms with lots of heat-generating equipment?
In those cases, artificial ventilation using fans or mechanical systems is mandated. This applies particularly to rooms containing industrial processes or heavy heating equipment to prevent the buildup of excessive heat or polluted air that could be harmful or uncomfortable.
Let's picture designing a small apartment in a hot, humid climate again. To rely less on air conditioning, the designer would really prioritize natural ventilation.
Definitely. They might strategically place windows on opposite walls to encourage cross-ventilation through the unit. They might also specify transom openings above interior doors, allowing air to circulate between rooms even when the doors are closed. These deliberate design choices, guided by the code's principles, directly impact occupant comfort and the building's energy efficiency, ideally reducing the need for constant mechanical cooling and fostering a healthier indoor environment.
The feel of a building's interior, the tactile world inside, is so defined by its materials and finishes. What kind of materials does the ID code specify or suggest for different elements like floors, walls, and stairs?
Chapter 5 of the ID code gets into these specifics, providing guidelines that balance aesthetics, durability, and safety. For flooring finishes, the options mentioned are quite diverse. You've got traditional wood planks, modern laminated wood, practical vinyl or rubber tiles, which often need antibacterial fungicidal treatment in hygienic areas like hospitals or kitchens, classic ceramic tiles, luxurious marble or granite, and various types of carpeting made from wool or synthetic fibers.
What about windows and doors?
Options include sleek, frameless glass or glass panels set in aluminum or steel frames. Different types of glazing are mentioned: plain, wired for fire resistance, or tempered for safety. Door panels can be solid wood or plywood.
And interior stairs. If they're made of wood, are there special requirements?
Yes, if wood is used, the treads and risers generally need to be made of non-combustible materials or meet a minimum thickness, like 2 inches. The supporting wood stringers also have minimum thickness and depth requirements to ensure they are structurally sound. For walls, partitions, and ceilings, the code lists various options like calcium silicate boards, structural glass blocks for visual interest, fiber cement boards, and different types of ceiling boards designed for acoustics, thermal insulation, or fire resistance. And even decorative moldings and trims are covered, mentioning materials like solid wood, fiber boards, extruded aluminum, preformed metal, or traditional plaster.
You mentioned earlier the emphasis on local materials in the Philippines. Does the ID code specifically highlight these?
It absolutely does. Section 33 specifically encourages the use of Philippine raw materials. It lists examples like bamboo for furniture and crafts, abaca fibers like sename or kinalac, for wall coverings, curtains, tablecloth, buri palm fibers, raffia, for wall coverings and cushions, coconut coir fibers for matting, carpets, rugs, and upholstery, rattan, specifically palisan, for furniture frames, seagrass or pandan leaves for wall coverings and mats. Even local leather is mentioned. It shows a real commitment to integrating indigenous, sustainable resources into modern design.
That's great to see. What about glass and glazing? It's such a common interior material now.
Section 35 covers this. It defines glass and outlines the basic types of clear glass. Traditional window and sheet glass drawn vertically during manufacturing, the very common float glass, made by floating molten glass on molten tin for perfect flatness, and high-clarity plate glass. Then it lists many variations: patterned glass, wired glass with embedded wire mesh, cathedral glass textured, obscure glass like sandblasted or etched, heat-absorbing tinted glass, reflective coated glass for solar control, and crucial safety types like heat-strengthened or tempered glass, which breaks into small, less harmful pebbles, and security glass laminated with plastic films. Key requirements include ensuring glass can withstand wind pressure, specifying minimum overlaps and clearances, and mandating impact-resistant materials, like tempered or laminated glass, for potentially hazardous locations like doors, large fixed panels near walkways, or enclosures around tubs and showers.
And finally, flame resistance is obviously critical for interior textiles.
Yes, Chapter 7 addresses this. Fabrics and textiles used in interiors must meet standards set by the DTI, Department of Trade and Industry, and the Bureau of Fire Protection. Fire-retardant finishes are often required for upholstery, curtains, wall coverings, and bedding. For commercial spaces like resorts and hotels, the use of inherently flame-retardant fabrics is strongly recommended. And naturally, all electrical wirings and lighting fixtures must comply with the relevant engineering codes and DTI safety standards.
Let's revisit that eco-resort example. The interior designer, guided by the ID code, might specify locally sourced abaca for wall coverings and furniture made from sustainable rattan to create that authentic indigenous feel.
Right. And for safety in the public areas, all the upholstery fabrics on sofas and chairs would be specified as inherently flame retardant.
And those large glass windows in the lobby looking out at the view, they would definitely need to be tempered glass to meet impact safety requirements, protecting guests from accidental breakage. It shows how the code helps designers blend aesthetics, local culture, sustainability, and stringent safety. Design isn't just about how things look or what they're made of, it's profoundly about people. How do our bodies, our sizes, shapes, how we move, influence the way spaces and furniture should be designed? This brings us to ergonomics and anthropometrics.
It's really fascinating stuff. This is where the science of human measurement directly informs practical design decisions to make things more comfortable, efficient, and usable for us. Anthropometrics is the study and measurement of human body sizes, proportions, reach, and movement capabilities. It includes collecting data on things like average height, sitting height, arm reach, waist circumference, even strength and physical capacity. Our sources specifically mention the average Filipino stature being around 1680 millimeter, that's about 5 feet 6 inches, which is a really valuable piece of local data for designers working here.
having that local average is incredibly useful, isn't it? So how does this anthropometric data translate into, say, designing better furniture?
Well, Chapter 6 of the ID Code gives specific ergonomic recommendations for seating furniture based on these principles. For comfort and good posture, it recommends that the seat of a chair should generally slant slightly downwards towards the rear. And the more the backrest reclines, the more important that slight backward seat slant becomes to prevent you from sliding forward.
Okay, a slight backward slant. What about seat height? Can it be too high or too low?
Absolutely. The code advises against seats that are too high. This can compress the underside of your thighs, potentially restricting blood flow, and it also makes it harder to plant your feet firmly on the floor, reducing stability. Conversely, a seat that's too low can cause your legs to stretch uncomfortably forward, again reducing stability, and it often makes you slide away from the backrest, meaning you lose proper lumbar support. Finding that just right height is key.
So let's take a practical example. An interior designer is choosing new task chairs for an office in Manila. Guided by ergonomics and anthropometrics, they would specifically consider that average Filipino stature. They'd look for chairs with an appropriate seat height range, maybe adjustable depth, and definitely incorporating that slight backward seat slant.
These choices, directly informed by anthropometric data and ergonomic principles from the code, aim to prevent discomfort, reduce fatigue, and promote better posture for the employees using those chairs all day. It demonstrates how human measurement directly leads to more comfortable, healthier, and ultimately more productive interior environments.
Designing responsibly today absolutely means thinking about the future. Sustainability isn't just a trend anymore. It's become a core ethical principle in good construction and design practice. How can the choices designers make actively help create healthier environments and more efficient buildings?
That's a vital question. How can design choices really minimize our impact on the planet and leverage natural advantages? It's about being smarter and more responsible with resources. The ID Code's Chapter 8 outlines key sustainable interior design principles. First, using renewable materials. It specifically emphasizes using indigenous, locally sourced materials as much as possible, which often have lower embodied energy and support local economies.
Then there's optimization, the idea of smaller is better. Does this mean designing spaces to be more flexible and efficient to minimize the overall building footprint and resource use?
Exactly. It's about smarter space planning. Constructability is another principle. This focuses on minimizing environmental disruption during the building process itself, reducing resource consumption, minimizing waste, and actively looking for ways to reuse or recycle construction debris.
Accessibility is also linked to sustainability here. How so?
It's about providing equal access for people with diverse abilities while also minimizing the project's impact on natural and cultural resources. It's a holistic view of respect for people and place.
That's interesting. What about future expansion?
Sustainable design considers the long term. It means designing for potential adaptive reuse with minimal demolition and waste in the future. Choosing materials and systems that can be easily disassembled, reused, or recycled later on. And recycling should be made easy for the building's occupants and operators too, planning for waste separation and collection right from the design stage.
And then there are the principles focused on climate and energy, natural conditioning.
This means using passive design techniques like natural ventilation, shading, and daylighting to achieve comfortable indoor conditions, reducing the reliance on energy-hungry mechanical systems like air conditioning and artificial lighting. And closely related is climate analysis. Designers should thoroughly evaluate the local climate temperature, sun angles, wind patterns, humidity, and treat these factors as potential assets to harness, like capturing breezes, or liabilities to mitigate, like blocking harsh sun.
Let's go back to that eco-resort concept. The designers, following these principles, would prioritize locally harvested bamboo and maybe reclaimed wood for construction and finishes, renewable materials.
They design guest rooms and public spaces to maximize natural cross-ventilation and use large windows or skylights for daylighting, reducing energy demand, natural conditioning. And they would incorporate clearly marked waste separation bins throughout the resort, making it easy for guests and staff to participate in recycling. It's about integrating sustainability into every aspect, from construction materials to daily operations.
Design really does engage all our senses, doesn't it? Often in subtle ways we don't even consciously register. The ID Code even touches on this, guiding designers to think beyond just the visual and create a more holistic sensory experience.
It's quite fascinating, actually, how thoughtful design aims to go beyond just looking good, to create an environment that feels comfortable and engaging on multiple levels. For the visual sense, established design principles like scale, rhythm, proportion, balance, and composition are used not just for aesthetics, but to help integrate the building harmoniously with its surroundings. The code even suggests using muted colors to help facilities blend with a natural context, unless there are specific functional reasons, like reflection absorption needs or strong cultural preferences for brighter colors.
What about sounds? How can design influence the soundscape?
The code suggests locating noisy service or maintenance areas away from primary public spaces, allowing natural sounds to dominate. Using elements like dense vegetation can act as natural sound baffles. Openings like windows or doorways can be strategically oriented towards pleasant natural sounds, maybe ocean waves, a flowing stream, or wind rustling through trees while trying to restrict or block out unnatural noises like traffic. And touch. How does that play a role? Design can encourage tactile interaction, allowing visitors to touch natural materials or cultural artifacts where appropriate. Varying the texture of walking surfaces can subtly define different areas or create different moods. Using contrasting textures can also draw attention to specific features.
And smell and taste. The code mentions these too.
It does. It suggests allowing natural fragrances from plants to enter spaces where appropriate, and ensuring that air exhausted from kitchens or utility areas is directed away from public areas. For taste, it even suggests providing opportunities, perhaps in hospitality settings, for people to sample local produce or cuisine, making the experience even richer.
Let's picture that visitor center at a nature park again. The design might feature large windows deliberately facing a scenic view with a babbling brook, bringing in both the sight and the sound of nature.
Inside, the walls might be clad in rough-sawn, locally sourced timber, offering a distinct tactile experience as people brush past.
The main pathway leading to the entrance could transition from, say, compacted earth to smooth wooden decking, changing the feel underfoot.
And maybe they plant fragrant native flowers near the entrance pathway, engaging the sense of smell. This multi-sensory approach creates a much deeper, more memorable connection between the building and its natural setting.
Okay, this feels like a really important culmination. Universal design. This is where design becomes truly inclusive, aiming to create spaces and products that work well for everyone, regardless of their age, ability, size, or background. A powerful philosophy.
It really is transformative, and it raises that key question. How does universal design go beyond just accessibility, which sometimes implies separate, special features to create environments that are genuinely equitable and intuitive for all users, right from the start? Universal design is defined precisely as a broad spectrum solution that helps everyone, not just people with disabilities. It consciously aims to avoid creating separate and stigmatizing solutions.
The ID code outlines 7 principles of universal design that really capture this philosophy. Let's quickly run through them. First, equitable use. The design should be useful and marketable to people with diverse abilities, providing the same means of use for all users whenever possible.
Second, flexibility in use. The design should accommodate a wide range of individual preferences and abilities. Think adjustable height counters or seating that suits different body sizes.
Third, simple and intuitive use. The design should be easy to understand regardless of the user's experience, knowledge, language skills, or even their concentration level at the time. Clear, straightforward operation.
Fourth, perceptible information. The design communicates necessary information effectively to the user, regardless of ambient conditions or the user's sensory abilities. This means using different modes, visual, auditory, tactile, providing good contrast, maximizing legibility.
Fifth, tolerance for error. The design minimizes hazards and the negative consequences of accidental or unintended actions. It should provide warnings or fail-safe features.
Sixth, low physical effort. The design can be used efficiently and comfortably with minimal fatigue. Think lever door handles instead of knobs that require tight gripping and twisting.
And seventh, size and space for approach and use. Appropriate size and space must be provided for approaching, reaching, manipulating, and using the design, regardless of the user's body size, posture, or mobility, ensuring enough maneuvering room, clear sightlines.
Beyond these core principles, the code also mentions specifics like graphic signs. The standard international symbol of access should be used clearly where facilities are accessible. And crucially for visually impaired users, Braille text should be included on key signage.
Color choices are also highlighted as important, especially for people with visual impairments.
Yes, the code recommends exaggerating lightness differences between foreground elements, like text, and their background, avoiding combinations of colors that have similar lightness levels, generally choosing dark colors against light colors, or vice versa, to maximize contrast. and being careful when using adjacent hues on the color wheel unless there's also a strong lightness difference.
Let's picture that public library example again, but through the lens of universal design.
Okay.
Instead of just having stairs at the main entrance, it would feature a gently sloping ramp alongside or integrated with the stairs, equitable use.
Study carrels or tables might offer adjustable height options, flexibility in use.
Wayfinding signs would use clear, large fonts with high contrast colors, universally understood symbols, and include braille text, perceptible information.
Doors throughout the library would have lever handles instead of round knobs, low physical effort, and aisles between bookshelves would provide ample maneuvering space for wheelchairs or strollers, size and space for approach and use. This holistic approach makes the library welcoming and functional for absolutely everyone in the community.
Wow, what an incredible journey we've taken today. We've really done a deep dive into this huge world of construction and design. We started right at the beginning, unpacking the fundamental definitions of construction as this intricate mix of art, science, and business, and how every building effort is essentially a unique, temporary project.
We did. Then we explored those core elements that make projects happen. The huge impact of the site and the user program, the strategic roadmap laid out by the schedule, and the absolute necessity of the budget, breaking down hard versus soft costs, and understanding why contingency funds are so vital. We even touched on the practical side, the tools, the equipment, and that fascinating layer of Filipino vernacular terms used right on the job site.
And we didn't stop at the process. We looked at the product, the building itself. We broke down its anatomy, looked at the structural frame and the different kinds of loads it has to withstand, and explored the various types of foundations connecting it to the earth. We also journeyed through the essential materials, wood, concrete, metal, plastic, and all those building boards, understanding their unique properties and why they're chosen for specific jobs.
And crucially, we spent a good amount of time navigating the regulatory landscape, using the National Building Code of the Philippines as a really detailed example. We saw how it governs everything from getting permits and undergoing inspections to mandating critical fire safety requirements based on construction type and location, even for specialized spaces. We also grasped how fire zones are a key planning tool for mitigating large-scale fire risk.
And finally, we moved beyond just the structure to focus on the human experience inside, guided by the ID code. We covered the importance of light and ventilation, the specifics of interior materials and finishes, the critical role of ergonomics and anthropometrics in designing for human bodies, and those vital principles of sustainability in designing for all the senses. It all beautifully culminated in that powerful concept of universal design, aiming to create spaces that are truly inclusive and work for everyone.
You know, understanding all these layers really does transform how you see the built environment. Every single building, every room you walk into is truly a testament to incredibly complex planning, rigorous regulations, and hopefully very thoughtful, human-centered design. It's this constant interplay between the vision and the practical realities.
So the next time you step into any building, your home, your office, a shop, anywhere, take just a moment. Consider not just how it looks on the surface, but think about those invisible layers, the intricate planning, the countless rules ensuring your safety, the deliberate design choices shaping your experience. What seemingly small detail, now that you have this knowledge, will you notice first? And what larger story might that detail tell about the incredible human ingenuity, collaboration, and care embedded deep within our built world?